Hello and welcome back to the Curves over Finite Fields, past, present, and future. And right now we're very happy to have Alain Couvreur speaking on how arithmetic and geometry make error correcting codes better.
Okay,
Please go
so
ahead.
mm, okay, so thank you, Rachel, for the introduction. So this is a follow-up of the talk I started yesterday, and before continuing, I need to mention that more or less I lied. I lied twice, so I just need to bring out the truth. First, first thing, and the first and probably more embarrassing lie was about Mariner. Yesterday I spoke about pictures of the moon, and actually there are pictures of Mars. The reason of that lie was that I promised Christoph a reference to Pink Floyd, and no Dark Side of Mars album has been produced by Pink Floyd. So I had to lie a bit, but here you have pictures of Mars. Actually, when Mariner 9 has been sent, a man already walked on the moon. So the program dates back 1971. Okay, so that was the first slide. Another one is about the abstract. So in the abstract of the talk, I proposed to speak about limits, theoretical limits of list decoding, and I started to make a part, so a little chapter about that, and it was horribly technical, so I preferred removing it because I was scared it would be a more boring. Not that the topic is boring, actually, the topic is excellent and fascinating, but it's just a lack from mine. I haven't been able to find a way to make it exciting. So I removed that, and the other fact is that I was scared that my presentation was too long because, as you observed, I already speak a lot. So I will not speak about that, but I will speak about other things. So yesterday I suggested uh, new issues. So yesterday I spoke to you about coding theory and algebraic geometry. So the use of algebraic geometry and number theory to make so great and exciting codes. And I had to speak about new issues about AG codes, and I promised component-wise products, things about component-wise products, also things about distributed storage. And since I did not find a way to tell you exciting things about theoretical limits on list decoding, I proposed an alternative questions about public key cryptography, which is another topic I like a lot. Okay, so let's move to this third part. So now I need to make a fast forward, like, okay, this way. So you remember the talk yesterday, la 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 la, and I was there. Okay, so yesterday I told you about decoding, and I spoke you about classical decoding up to half the minimum distance. And my last point was that, in some sense, what makes decoding efficient for code on curves is the fact that we start from a nonlinear problem and then linearize it, and the fact that actually linearization works because when linearizing, in some sense, we consider, instead of considering a Cartesian product, we replace Cartesian products by tensor product or some quotient of tensor product. And the point is that here, by linearization, we are considering spans of products of two subspaces of some function fields, and these subspaces are Riemann-Roch spaces, and the span of the product doesn't grow too much. And this is what makes decoding of Reed-Solomon codes and then codes from curves efficient. Um, then I explained also that Cutter and Pelikan, almost 30 years ago, proposed a fully abstract description of decoding, not in terms of product of spaces, but directly in terms of component-wise product of codes. And here again, what they show is that in some sense, if you have codes, a code C with another code D such that the product is not too large. So the component-wise product, the span of all the component-wise products is not too large. Probably there is an efficient decoder. And this moves to the question, what kind of codes permit to have small products? And just a simple version of the question is at least what kind of codes have a small square with respect to the component-wise product. So you take a code, you consider all the span of all the component-wise product of two vectors of the code. And so for a random code, it will be a huge thing. In general, you will fill in the ambient space, or if you have a very low dimensional code, you will have a code whose dimension is mostly, yes, half the square of the original dimension. And the question is, which code have a small square? And by small, basically, we want the growth of the dimension to be mostly linear in the original dimension. And as I said, this can be since we are considering codes from curves, the same question can be considered in a more abstract setting on the level of function fields, and we can ask about which subspace of a function fields, or more generally of an algebra, do satisfy such an identity. So the dimension of the square of the space, that is the dimension of the span of all products of two elements of the space, is not too large. So basically twice the dimension plus some extra term, which is in the worst case also dimension of S, a bit less than dimension of S. Okay. So in this context, first on the level of function fields, I could cite a contribution of mine, which so in a common work with Bashok and Zemmour, we consider the following settings. So we took a field, a finitely generated extension of a perfect field. So let's say, think about a function field of a variety, but not necessarily a curve. So yes, non-zero positive transcendence degree. And I take a finite dimensional subspace of that big field, which spans the field. It's an important fact. And the question is, if the square of that code, of that space, so it's no longer code, is not too large, what we can prove is first that the field, the original field, has transcendence degree 1, so it's the function field of a curve. And the second thing is that we are able to say for very particular value of this gamma that the field will have genus 0 or 1. And actually what we expect, our objective, is to prove that actually, yes, our conjecture is that in the general case, once we have transcendence degree 1, then the genus of the field will be bounded from above by gamma. And for the moment, we are not able to prove that, but we're still working on it. So this is a kind of striking result, because what it says is that if you have a space which generates the field, only quadratic relations between functions, in some sense, determine the geometry of the underlying object. Here, just the fact that all the products span a small space permits to decide that it was actually the function field of a curve. So, as I said, still an open question for us. We are not able to bound the genus of the function field in general, only to say it's a function field of a curve. And the second question is now, how to go back to codes. Here, I just considered the abstract setting of subspace in a function field. And yes, what about codes? So what about codes from with a small square. And here, in some sense, we have the idea that spaces in a function field which have a small square actually span a function field of transcendence degree 1, so a function field of a curve. So it's natural to ask whether codes with a small square could or not come from curves. So are all codes with a small square come from algebraic geometry and from algebraic curves? So what can we say? Actually, it's possible to have a geometric interpretation of this square. That is, you start from a code and you consider a generator matrix, so a matrix whose rows span the code. So here we could consider a basis of our Riemann-Roch space, and then the rows are evaluations of the elements of this basis. And then the idea is interpret columns as points of projective space of dimension k minus 1. So this is, if you start from an algebraic geometry code, actually what you get is the images let's say you start from an algebraic geometry code associated with a very ample divisor. Then you have naturally full embedding, so not rational, but regular embedding from X into projective space of dimension k minus 1, if k is the dimension of your Riemann-Roch space. And this embedding can be made explicit using the basis f1 to fk. And here, these columns will correspond to the coordinates of the images of the PIs by this embedding. And then we suppose the code has a small square. So here we could consider the symmetric square of our code, and there is a natural canonical projection, so natural surjection from the symmetric square of the code into the star product of the code by itself. And if you look at the kernel of this map, of this canonical map, actually what you have is a space of quadratic relations applied on which vanish on all the columns of this matrix. And so in some sense, you have the space of quadratic forms which vanish at my point PIs with respect to this embedding. And if we look at the corresponding variety, so at the variety corresponding to the space of quadratic forms, we get a variety which, if we start it from an algebraic geometry code, contains actually the curve. And it has been proved that under mild considerations on the degree of the divisor, actually, we get back exactly the curve by considering these quadratic forms. So this is a result which is based on former works by Mumford and Saint-Donat, which basically say that if the degree of your divisor is large enough, your embedding, the corresponding embedding, is obtained only by quadratic. The corresponding embedding is obtained as intersection of quadrics. Okay, so but now what about a code which is not supposed to come from a curve, and it's not a priori supposed to come from a curve, but which has a small square? Oh, okay, so what would be exciting would be that we could actually prove that the code actually comes from a curve. So it was not supposed to come a priori from a curve, but the constraint having a small square would provide naturally a curve and would tell us actually there is no other way to get codes with small square than using algebraic curves. The limitation we have, which does not permit actually to conclude and does not permit to use what we did about function fields, is that, okay, you think about your Riemann-Roch space. And your Riemann-Roch space maps canonically into your code. And in terms of the previous embedding, your Riemann-Roch space can be interpreted in terms of forms of degree 1 in my projective space. And now I could consider forms of degree 1 restricted to my mysterious variety. And actually, if that variety was irreducible, then my Riemann-Roch space would identify to some subspace of the function field. But to have a function field, I need irreducibility. If I had elements to say, okay, the variety here is irreducible, then using the previous work with Bashok and Zemmour, we would be able to prove that the corresponding code actually comes from a curve, which would be great. But it's not that nice because actually there are situations where irreducibility is not satisfied. Think about this example. You consider the union of a plane and a line not contained in a plane in P3. And you consider the code obtained by evaluating linear forms at all the points of this union of a plane and a line. Then, okay, it has dimension 4, which is a dimension of space of linear form over P3. And if you think about the square, actually, you would get dimension 7, which is twice dimension of C minus 1. Why do we get dimension 7? We just have to think about what's the dimension of the space of quadratic forms vanishing at V. And basically, such a quadratic form will vanish on the plane and vanish on the line. And we just have to understand what is the dimension of the space of hyperplanes, so of linear forms vanishing on the line, and it has exactly dimension 3. So the dimension of the symmetric square of C is dimension of the symmetric square of a space of dimension 4. It's 10 minus dimension of a kernel, which will have dimension 3. So we get dimension 7. And here, if we compute the variety corresponding to my ideal of quadratic form, we get back my original variety. So it's this union of a plane and a line, which is reducible, of course. So here we have an example. So maybe it's a kind of critical example of code whose dimension of square is less than doubling, and actually it is associated to a variety which is reducible. So still an open problem. Okay, so in summary, for this problem, there is this question, how to classify codes whose square is small. So here, I remind you, square, by small, I mean dimension of the square is twice the dimension of C, minus 1 plus some corrective term gamma, which should be less than dimension of C, more or less. And as we see, a geometric direction would be to understand this variety, which in a paper of Randri and Bologna is called the quadratic hull of the code. And the question would be, what kind of additional hypotheses could be made to expect an irreducible, such an irreducible variety? If we had that, we could conclude that nothing more than curves permit to get such mysterious codes. Okay, so now I'm start to be a little late, and I will move to questions about public key cryptography, and I will start to get a bit faster. Okay, so public key cryptography, so public key cryptography based on code is more or less as old as RSA encryption scheme. So it dates back the late 70s. And I will not describe Macauley's system, just saying that its security relies on the hardness of decoding and also the hardness of distinguishing some code I can decode with a random code. So all the difficult part to instantiate it is to exhibit a family of codes, for which we have efficient decoders, but whose structure can be masked in order to do as if they were random. Okay, so why do we speak about public key code-based cryptography today? The advantage, the node advantage, is that it is claimed to be post-quantum, and it is also faster than RSA in terms of encryption, and in particular in terms of decryption. And the major drawback, which is considered, is that it requires, to assert a good security, it requires very large key sizes, more or less 1,000 times larger than what we can expect for RSA for the same level of security. Okay, and why do I speak about that? Because there have been a lot of families of code which have been proposed to instantiate public key cryptography using codes. And in 1996, in a short paper, Yanmo and Moreno proposed to use AG codes. More precisely, they proposed three different approaches: AG codes with no particular additional features, or concatenated AG codes, or what is called subfield subcodes of AG codes. So you take an AG code over some finite field extension and you make expurgation, so you keep only code words which are in some subfield. Okay, actually, it has been proved that the raw use of AG codes is unsecure, and also concatenated code in general are unsecure. About the raw use of AG code, actually, the attacks appeared in 3 steps. So the genus 0 case, Reed-Solomon code, was broken in 1992. And then low genera have been also broken in 2009 in a similar manner. So both attacks here rest on computation of low weight code words, and then and the fact that minimum weight code words are easily computable for such codes, which is not a feature satisfied by random codes. And then for arbitrary code, we propose another paradigm of attack, which proved that actually for any genus, those codes are unsecure. And if I speak about that, actually, it's strongly related to previous questions. Actually, these codes are weak in terms of cryptography because those codes have a square which behaves very differently from that of random codes. They have 2 small squares, and this provides us a way to distinguish these codes from random codes. And from this distinguisher, it's possible to derive an attack. So here, this leads to another question. So if you look at here, it seems that the third proposal, so subfield subcode, still resist, and actually the genus, even the genus 0 case, is that of so-called Michaelis, a classic Michaelis proposal, which is now on the path to be standardized by NIST. There is this question, actually, what about considering arbitrary genus? So it would provide a generalization of the classic Michaelis setting, and it seems to be strong and resistant to any attack. So if we look at that, there are several questions that could be asked. I mean, we think about codes over some extension, and then we restrict to some subfield. So what kind of degree of extension degree should be chosen? So the larger the extension degree, the worse the key size, but also the best the security. For genus 0, it has been observed that a low extension degree provides a low security. But if we take a large extension degree, as I said, we have huge key sizes. And then there is another approach to reduce key sizes, which has been considered by a former PhD student of mine, Elise Barelli, who consider to reduce key sizes, considered codes with non-trivial automorphism. If you have that, so the public key is a basis of a code. But if you have a non-trivial automorphism group, you can replace your basis by a basis over the group algebra. And so in some sense, you reduce the key size by a factor, which is the size, the cardinality of the automorphism group. And how to get codes, algebraic geometry codes with a lot of automorphisms? Use curves with a lot of automorphisms. So what kind of good choices can we make in terms of curves with automorphisms, in order to have good trade-off in terms of security and key size? And this is still a question. This is still very interesting open question on which we could think about. Um, Last but not least, I suggested to speak about codes for distributed storage. So I found a very nice picture, which has absolutely no interest, but being nice. And question, what about the recent development of cloud storage and how algebraic geometry can be interesting for application to cloud storage? So, as I said yesterday, in cloud storage, so in a cloud, your data, your personal data, is distributed over a lot of servers. And these servers, so the contents, so the data should be accessible at any time, but some server could fail, be subject to maintenance operations. So when a server fails, it needs to be immediately replaced by another one containing the same data or similar data. And to reconstruct such a server, this reconstruction operation will be made a lot of times, so we have to limiting the consumption of power. And our model would be that you think about your data to be encoded, and each server carries one symbol of a code word representing a file or your file or a part of your file. And the question is how to reconstruct a symbol of a code word while considering only a limited amount of other symbols. So if you consider Reed-Solomon codes, which are the most famous one, it turns out that they are very bad for this question because for a Reed-Solomon code, as I said, so it's obtained by evaluating polynomials. And if you want to get back the evaluation of the unknown evaluation of a polynomial of degree k, you need to know at least k other one evaluations to perform Lagrange interpolation. So for such code, if you have one symbol which is erased, you need at least k other symbols to reconstruct it. And this cannot be worse, actually, because the code has dimension k. So k symbols means considering actually the whole code words, more or less. So this leads to, so Reed-Solomon codes, which are excellent for a lot of applications, actually are very bad for this setting. And this leads to the definition of LRC, so locally recoverable codes, which are codes which has the following features. If you take one position, for any position, I, there is a small subset of position such that if you consider all these limited subset of positions, then you can recover the unknown position I. So you suppose your ith position has been erased, then by considering L neighbor in some sense positions, then you can recover the lost data. And for such codes, exactly like for general codes, you have a singleton-like bound, which take into account the locality, which is the amount of neighbor symbols you have to query in order to recover a lost symbol. So notice that if your locality is the worst possible, that is k, then you get back exactly singleton bound. But for a larger L, you will have something which is worse. So, but we could look for a fixed L for some optimal. And Tamo and Barg propose a way to reach that optimal. The idea is the following one. So how many time do I have left? I'm scared.
About well, like 5 minutes.
5 minutes is okay. Thanks a lot. So Tamo and Barg make the following construction. So their construction is somehow derived from Reed-Solomon code, that is AG codes from a curve of genus 0. So they take the projective line and some order L plus 1 automorphism. Think about multiplication by a primitive Lth root. No, not that. It's wrong. It's elevation to the L's power, so to the L plus 1's power. No, sorry, no, it's this. It's an automorphism. You take this is true, the multiplication by L plus 1th primitive root of unity. So this is an automorphism. And then you take an invariant polynomial with respect to this automorphism. So for this example, you think about the elevation to the L plus 1th power, which is clearly sigma invariant. And then you will consider a union of sigma orbits, and this will be your evaluation point. And you will evaluate functions at points of this union of orbits, but these functions are no longer elements of a Riemann-Roch space. In some sense, they live in some particular space, which is defined here. So you look at functions which are polynomial in X and also my sigma invariant function. So why doing this? Think that your orbits will be your recovery set. So if you lose one symbol, you will ask other symbols corresponding to the same orbit. And the point is that if you restrict to some orbit A, then your function G is constant, so is a constant on this orbit. And by this manner, the function restricted to the orbit looks like a polynomial, but a polynomial of very low degree. Here, think that G has already a degree L plus 1, and so you have a degree which will be up to K. And by this restriction to an orbit, you have some degree collapse. And this degree collapse permits, when restricted to one orbit, to have some local code in which you will be able to perform recovery. So degree collapses, and actually this proposal made by Tamo and Barg permits to reach the previous singleton-like bound. But with the classical limitations is that, it's derived from its Solomon code, and so you have a limitation on the length of the code with respect to the alphabet. And if you want to avoid this limitation, we need to move from rational line to curves. And so what's general setting? You just consider a Galois cover of a curve, and you will consider, so your recovery sets will be fibers with respect to this Galois cover. So Galois invariant sets. And what we'll take is functions whose restriction to fibers can be interpreted in terms of polynomials of low degree. So this leads to the following description, which are, so you take fibers of points of X, which are totally splitting, and this will be your invariant, so your orbits, and you will take some divisor on X, and actually we do mostly the same. So we need to choose at some moment, and this is probably the most disappointing fact, we need to choose some primitive element of the corresponding extension. And we do actually what we did in the previous situation, that is, we will consider functions which depend on powers of this primitive element. So this is a non-constant part on fibers, which would be of low degree, and then multiplied by functions which are pullbacks of functions on X, so constant functions on the fibers. And by this manner, it's possible to have good trade-offs between a good minimum distance close to that singleton-like bound and longer code for a fixed finite field. So what else? Actually, we made it for surf curves. It's possible to extend that to any Galois cover. So for instance, Galois covers of surfaces, which has been proposed in 2017. Recently, Salgado, Varilli Alvarado, and Voller proposed some fiber surface point of view. So it still codes from curves, but with some fiber surface point of view, which gives additional and a better understanding of what happens. And here I considered only single recovery set. So I have a point, so I have a position, a lost position. I have only one way to recover it. But sometimes we could be interested in recover it in a lot of different ways. And for that, it's possible to consider fiber products of two coverings. And if you have fiber products, and if you look at fibers, then the fiber of a fiber product is a product of the fibers. And the idea is that you have two different recovery sets here. You can consider vertical recovery sets in this product of fibers or horizontal recovery sets. And by making a fiber product of n curves, then you have n manners to recover. So this gives you what is called availability. So last questions here. First, we had this description of our code, which involves the choice of a primitive element. So is there a fully geometric interpretation of this? I don't know, in terms of codes from pullbacks, so from a vector bundle, or for some pullback, so push forward, let's say, of some line bundle of the upper curve. I don't know, but it's, from my point of view, a bit disappointing to have this choice, so this non-canonical choice of primitive elements. From my point of view, is not completely satisfactory. Maybe there is no better way to do, but I would be interested to have a fully geometric interpretation. And then on the other hand, so all this construction seems to be relied to fiber products on curves, or fiber products of curves and finite sets. And is there a purely coding theoretic description of these constructions? Is there a fiber product in the category of code which could permit to have a fully coding theoretic descriptions, exactly as it has been possible for the setting of in the setting of decoding, to fully abstract the decoding algorithm? And in terms of recovery sets, why not considering surfaces and considering for a given point, considering any curve crossing this point as recovery set, so which would permit to have much more availability? So is it a way to get better, to get yes, locally recoverable code with a lot of recovery sets? And this is an open question from my side. I have no answer from that to that, actually. Okay, so a lot of questions, a lot of answers, a lot of other questions, and I'll stop there. And if you have other questions, feel free to ask. Thanks a lot for your attention. Sorry for having been this long.
Great. Let's see any questions here. Well, maybe I'll start with one. Have people ever used non-Galois covers, like, for instance, covers coming from Bailey maps in these codes?
I'm okay. So maybe I should have checked better. In particular, I don't know if one of the authors of the first paper above is in the room. I'm not fully sure that they requires the cover to be Galois. And actually, in the full description, let's look at this. Yes, it's unclear to me that you need the morphism to be a Galois cover. I may be wrong, but I would say that you have straightforward generalization with non-Galois cover. I may be wrong, so I suppose I don't swear.
Oh, thanks. Well, let's see. Are there some other questions?
Check. Where's the chat? Ah, yes, I cannot see the chat. Shall I stop sharing?
There's a joke. There's a joke in the chat about Britige's law.
About that? Oh, I need to check the joke.
It's about the question mark in the title. Oh, Elisa has a question.
Yes, please, Lisa.
Actually, I have kind of two questions. So the first one, somehow I asked in the chat. So it was this thing about that I read somewhere that actually like all codes can be made from curves. So they are AG codes. But then somehow you say that sometimes there are things that are easy to do with these AG codes and there are things that they are difficult to do. So I guess, so correct me if I'm wrong, the point is that it is difficult if I give you a code, so for you to give me the presentation as an AG code, right? I mean,
it's not exactly that. Actually, it's a bit more tricky because the original, I think so this story that any code is AG code is in several steps. As far as I remember, Gopa first observed that, but with the wrong proof. Basically, the idea is the following one. You start, actually, it's not that different than from, okay, wait a minute. Yes, start from, you have a code, you start from a generator matrix, and then you interpret any column as a rational point in projective space of dimension k minus 1. And then you take a curve which passes into all those points. And here you have, your code can be interpreted in terms of evaluation of linear forms, so the h0 of O of 1 at points. And then the idea is just restrict this shift to the curve, and you would say, okay, it's a code on the curve. I think later on, Lachaud noticed that we should take care of the fact that the curve is not necessarily projectively normal, and maybe the restriction of the sheaf is so that restriction of global sections are not all the global sections. So you need to have some projective normality additional constraint. And I think it's about in 1990 that Pélican, Chen, and we proposed construction with this projective normality setting. And actually, it's very brutal what they do, because they introduce a curve which catches all the rational points of the projective space. And this is actually completely constructive. But what you get, and why it's disappointing, is that you get a code which is described from a curve and a divisor. But if you look at the lower bound, so the estimate you will have from the minimum distance, you will observe that basically it will tell you that the minimum distance is lower bounded by 0, or actually even some negative integer. So it tells nothing. And later on, if you try to apply a decoding algorithm, it will correct 0 errors. So actually, from my point of view, it's interesting from a philosophical point of view to know that any code can be realized as algebraic geometry code, but you will do nothing interesting with that. And actually, if we were able to do something interesting with that, probably we would be close to prove that P equals to NP, or something very surprising like this.
okay, thank you very much.
You're welcome.
I see the what is the difficulty. And I mean, somehow also related with this, because you just said that the AG codes that comes from curves, they are not good for crypto. Well, I mean, when you do the restriction of scalar later, yes, but like in general, just like this, they are not good for crypto because they are attacks. So I was wondering if those attacks are also useful for AG codes that come from higher dimension varieties.
I don't know. Probably they will not. I would say that since the crux of the attacks is relates to the behavior of this star product, the attacks will be less efficient because such codes have much larger star products. But also for these reasons, these codes are, we do not know efficient decoders for such codes, and decoders are the decryption function in Macaulay schemes. So if you don't have decoder, you cannot instantiate it with such code. So maybe they would be resistant, but we don't know how to use them.
Okay.
In some sense, codes from surfaces and higher dimensional varieties are interesting also for these storage questions, because for this storage question, we do not care about decoding, actually.
Let's see, there's a question in the chat. Alexander, do you want me to read that, or do you want to read
I can read. Yeah, thank you. Very nice talk. I just have a question. Have you seen people considering codes that would allow error correction not in the worst possible case, so to speak, but just for most, specifically for the purpose of cloud storage. If you don't need to. I mean,
So here you think about global decoding. I mean, you have you do not consider local recovery, really global decoding. That's the point.
local recovery, but not necessarily like the worst case scenario. Like for most,
it's a good question, actually. As far as I know, so I could not claim that I know all the literature on locally recoverable codes or regenerating codes, which is another paradigm. But as far as I know, all the thing I saw was worst case reconstructions. So yes, the question of having code with efficient reconstruction in average, I'm not sure it has been considered, but in some sense, I don't know. Does it really make sense? I mean, what you would consider is you would say that almost any position could be recovered from a few other ones, but you would just have n of them. So I mean, what you would have is yes, an expectation of positions which are recoverable, which is linear in the code length. I don't know if yes. I don't know. So
yeah, I'm just wondering if there's any real difference. I'm just wondering if there's any real difference, like if you know the parameters get bad because you want to make sure that in a worst case scenario things still work, or it doesn't really matter. Like a good code is a good code no matter what, so to speak.
I don't know. I should think about it. It's I don't know.
Well, thank you. Thank you.
You're welcome.
Oh, great. Well, let's thank Alain again.
Thank you. Thanks again for this invitation.
We'll take a 10-minute break now. And return on the hour.